Hey everybody. Cool. We're going to get back to simulating a quantum computer in Rust. And in particular, last time we hit what seems to be a performance bottleneck, but it's a very strange one as we started to work towards Shor's algorithm. And so I wanted to take this opportunity to kind of talk about the general thought process for how to find bugs, how to find performance bottlenecks, and then walk through it and hopefully resolve this one, which should be fairly easy to resolve given how strange it is. The stranger things are, the easier to resolve they usually are, in my experience. So the basic issue here, if you remember, is that if we try to run this test where we try to do an order finding algorithm on the number 6, which should be, extremely simple, but of course we know that this quantum algorithm for finding factors is not going to be super efficient. That's the whole thing about simulating a quantum computer, the classical computer. But for small numbers, it should still be fast. And we can see that this test has been running for several seconds, and I don't think it's ever completed in the time that I've tried to run it. And that's this is basically without running the algorithm at all, since we were stubbing out a bunch of things in here. So right now the way that the algorithm works is it just instantiates the two registers. It instantiates the order finding circuit, or I guess the order finding circuit has already been instantiated, and it tries to run it. And that order finding circuit is just a big Fourier transform, a big inverse Fourier transform, and a big identity, not in that order. And the place that it's getting hung up is on this big identity gate. Obviously, this identity gate won't be an identity gate in the actual algorithm, but I was just trying to stub out the general structure of the algorithm, and we started hitting this performance bottleneck, and it's happening here. I was able to walk through the debugger and see it happening here. The thing is, n qubits is 6, I think. I'm pretty sure. And so 2 to the n qubits, 2 times n qubits is 12. So this is an identity. This is essentially a quantum gate. It's just a matrix, a square matrix. So this is essentially a identity gate on 12 qubits. Oh, and I'm actually realizing something immediately, which means that it's a identity matrix on 2 to the 12, which is big. 2 to the 12 is 60,000 or something. I think. I don't remember. My powers of 2. Okay, so that's immediately something that I had kind of overlooked last time, is that, of course, the number of qubits is not the number of basis factors. If you have n qubits, that means, if you had 3 qubits, that would be 0, 0, 0, 0, 0, 1, 0, 1, 0, right? It goes, to list all of them, you'd have to list 8 of them, all the combinations, all of the strings of zeros and ones that are 3 long. And in the same way, if we have 12 qubits, that's 2 to the 12 matrices, which is going to be big. So what's the general approach here? Well, the general approach is going to be to find we want to bound where our bug is. So this is performance bottlenecks, and bugs are kind of the same thing. You need to locate what's causing the problem first, and in order to do that, you have to first guarantee that the problem is somewhere where you can find it, somewhere you're looking. So you need to bound the problem by making sure that you haven't narrowed your focus too much. And then you basically want to split the problem in half over and over again. It's like a binary search in order to find where it is. So the first thing to do, and I've done this already, so we know the problem is sort of to the right in some sense, or deeper than this quantum algorithm. And in fact, we've drilled into the debugger, so we kind of know where it's happening. And I think I already did a test in here somewhere. I think I did a test identity. Thought I did. Test. Am I crazy? I really thought that I had already done an identity transform. Hey, Alpha Ha, thanks for the follow. Appreciate it. We're simulating a quantum computer, and at the moment we're trying to chase down a performance bottleneck that I suspect is due to trying to instantiate a 60,000 by 60,000 matrix. Now that I'm starting to look at it, but we're gonna try to actually chase it down. So I thought that I had already done. Oh, maybe it was in here. Quantum gate, controlled phase shift, C naught, identity. Yeah, okay. Okay, so here's an identity matrix on 6 qubits, and it runs pretty fast. If we make this 12 qubits, yeah, this is what I did already. I think I ran it at 10 qubits, and it ran in about 3 minutes. Which is surprising. So I'll kick this off and just let it run in the background, but we should be, I think we should be surprised that it takes 3 minutes to instantiate a 2 to the 10 by 2 to the 10 matrix in an algebra. But maybe it shouldn't be. So that sort of bounds the problem from the top or from the left, however you draw the mental picture in your head. The idea is kind of, right, maybe you have some right, like you have code, your code paths kind of look like a tree, right? And so you kind of have something that's like XYZ, and it's hard to draw a tree in a text editor, but like you have this big tree that has all these branching paths, and it can be really complicated. And we know that we have a bug at the top of the tree. First, we need to prove that we have a bug, or we don't have a bug at the bottom of the tree, and that'll tell us that, oh, okay, the bug is somewhere in the middle. And then we want to start cutting it in half. So we would want to then test it, here, say. And if it's up here, we'll look up there. And if it's down here, we'll look down here. And if this is a big tree with a whole ton of elements in it, then it'll take something like the log of the tree steps to find where the issue is. Now, you can do better than that if you think about it in terms of probabilities, right? So, like, I have some... This would be, if I assume that the bug or the performance bottleneck can be anywhere in these, 6 layers of the tree, then I should just binary search it. But if I have some sort of Bayesian belief about where the bug might be in the tree, like, for instance, in our particular case, I suspect that the performance bottleneck is due to the size of the matrix that we're trying to instantiate. So I can sort of... That biases me towards that area, and I should, instead of trying to just split the tree in half in terms of levels, I should move it to split the probability in half of where I think the issue is. So let's do that. So first, though, we need to, like, prove that the problem, we know where the problem is. And so the easiest way to do this in this case, where the issue sort of seems to be with the library, but I don't think it actually is with the library, is to just create a brand new Git repo and a brand new repo, just pull in that one dependency, and then make sure that the problem isn't there. So I just quickly before this created a brand new repo, pulled in an algebra 0.31.4. I meant to check. That's actually not the same one we have here. And also our test ran in 143 seconds, so like 3 minutes-ish. So I'm gonna update this to 31.4 just to be super consistent. And then I'm gonna run that test a second time, which my machine does not want to do. Let's rebuild it. Oh, there we go. Now VS Code gets excited. It waits for lock on the build directory. Okay, so we'll let that run. Meanwhile, in here, all I did is instantiate a matrix. But what I did wrong is that I needed to do 2 to the 12 here. And I'm going to do 2 to the 10 to be consistent. And see how long this takes. Okay, it failed immediately because I didn't put the right vector into it. Instantiated that. Okay, so that ran, even though it's a 2 to the 10 size matrix, that ran super quickly, right? It ran in a quarter of a second, which is what I would expect because it's like not outside the realm of possibility that you can have matrices of this size in like, you know, machine learning and applications, and I would expect this dependency to be able to handle that. So what have we done? We've proven that the bottleneck is not in the dependency. It's not. If I just instantiate the matrix, then it works as expected. Meanwhile, here we are in our test, taking more than 60 seconds. So, do I have any beliefs about where the bottleneck is? I mean, I believe that it's in between the two places that I've tested, but I don't have a super strong belief. So, the next thing I'm going to do is try to bifurcate the problem, and the only really good way I have to do that at the moment is I've done this test on Quantum Gate. I should really be doing this on the type inside of Quantum Gate, which is the square matrix type, which is just a wrapper for an algebra. So I am not like my it's strange, right, that all I'm doing, all this square matrix type does is wraps. That's not square matrix. Square matrix. Square matrix. All of this type does, it's just a convenience type for me that wraps a matrix of complex numbers. I would not anticipate it being any slower. Like Rust has zero cost abstractions. I would not anticipate it being any slower. So, while I'm at it, I'll fix some redundant dependencies. Okay. So, let's take a look. Oh, what? It said it was never used. Okay, I'm gonna move. Alright, let's fix some things. I don't really like having my dependencies in my tests like that. Maybe it's fine, but these are being double imported. That I wouldn't think would need to be there at all. And I actually never use float comparison, so I'm going to go ahead and remove that from my thing also. Okay, I do have unit vector 2 in here. Why do I do it this way? Test instantiates complex vector. Okay, this is literally not a type I use anymore. That was from back when we did and same story. Yeah, we don't do this anymore. Okay, cool. Nice to clean up a little bit while we're in here. Let's go ahead and commit that. Some unneeded dependencies. Oh, actually, let's also, we never use float compare, so I can get rid of that entirely. Now, remove unneeded dependencies. Okay. Okay, so back at it. So we should have a test in here that shows that this is fast. Semantic tokens folded. Okay, I don't know what that does. I don't think I care. Test square matrix instantiates. And we'll do let matrix be square matrix. Actually, let's just call this square matrix identity. And let's do 2 usize power to the 10th. Sure. Matrix dot size is to the 10. V can be a D vector. Yeah, sure. Interesting. Okay, that's fine. And sort of matrix times just V should be fine. I don't know why I'm norming anything. Is V. Can't multiply a square matrix by a vector. This is not a thing we already do. I feel like this is a thing we already do. Did I miss a parenthesis somewhere? What's happening here? Yes, I missed an end bracket. Assert size. This can be assert equals. I wonder if it's. Am I calling is unitary? I'm actually going to get rid of this. And I also want to check my test. Okay, I'm not doing is unitary. Do I do that? New normalize. Okay, this is something worth testing, is that the thing I'm running in my tests is that I can apply the gate to quantum registers, which involves computing the basis, which should be cheap, and it involves applying, which does vector multiplication, which I would also think would be fast, but there are places in there that might be the bottleneck. So we're starting to form some Bayesian beliefs about what might be going on here. Okay, matrix cannot be multiplied by a D vector, says the right size. Sure. Let's look. Matrix. Okay, so we do multiplication by matrices. We do multiplication by unit d vectors. We never did multiplication by d vectors, so that's fine. That's fine. Let's just do. Can I put unit around this? Let's see here. Unit d vector. Complex F32. New normalize. That's fine. And we need turbofish somewhere in here. Okay. And then we can't do equality. Is that the issue? Mismatched types. V is a unit d vector. Oh, matrix of V needn't be a unit d vector? Is that true? I would think it would be. What did I define it as? I output a d vector. Oh, don't I need to output a unit d vector? Not necessarily. Is my thing ever not normalized? It's really always normalized. Sorry, I'm thinking out loud. I don't really know why I wouldn't output a unit d vector here. Okay, which just does not instantaneously work. I assume I can't do this. That would be crazy. Yeah. So I'm doing a matrix, which needn't be a unit matrix. Again, why am I not just making this a unit matrix? Okay, there might be a reason to do some refactoring here. To enforce unitarity. So unitarity just means the probabilities of the system being in some state had better always add up to 1. Like the system had always better be in one state, and so we want all of our matrices to be unitary and all of our vectors to have unit length. Okay, but it doesn't like this because this is a unit vector. But we should be able to say d vector new normalize, or maybe just from new normalize. What happens if I do this? Okay, and then the only issue here is that we've moved it. We don't really have to clone twice, but it'll save me needing to clone later if I add more tests. Okay, so the other thing that's worth thinking about is like what we expect to happen here. And I guess I expect it to take more than a quarter second, which is what it's doing. But this immediately rules out one type of bug, or one type of performance bottleneck, which is like the issue isn't that in our the The bottleneck isn't in applying these gates, right? Because in the test we were doing before, we're applying the gates. We were like, oh, maybe that's where the bottleneck is. Maybe it's not in doing the identity. But indeed, we're not applying the gates at all. We're doing this one multiplication, but we're not applying the gates. So it seems unlikely to be that. And we could step through the debugger and see. I'm pretty sure the issue is still in here, if I had to guess. Okay, so it's interesting, right? Because we have this test that runs in 1/4 of a second. Which looks like it's doing a lot of the same things as this test. I'm going to kill this test because I don't want to wait for it. I'm going to just check the size. Okay, and again, it takes a long time, so the issue is in instantiating the identity. All right. So what do we do when we instantiate the identity? We create a new unitary matrix from the identity matrix. And when we create the new unitary matrix, what do we do? We calculate the determinant. Right, so I totally forgot that we wrote this function. This is our function for forcing things to be unitary. And we do a bunch of stuff in here that we didn't worry about when it wasn't a performance bottleneck, but now we have to worry about it. So let's go back into the debugger. So now we're starting to have a pretty strong feeling for what the issue might be. So let's go into the debugger. Is my test still running? My computer is like humming away. Doesn't seem to be though. And let's step through and see where we run into issues. Okay, matrix is square. That should be fast. That is fast. The determinant norm. So we're calculating the determinant, we're calculating the norm of the thing. I suspect that the determinant is really slow. And I suspect this because we have a 60,000... How big is our matrix? Wait, why is our matrix only 4? Hang on. Oh. I get it. Okay, I'm gonna kill this. We can't, when we instantiate this, it should be fine. I don't understand why it only thought that the matrix was 4. Okay, there we go. Okay, so there's a million entries in this matrix, and when you calculate the determinant, you have to calculate the determinant of every n minus 1. You basically go recursively into this thing. So you calculate, so 1,485,776. you calculate the in order to do that, you have to calculate that many determinants of 1,048,575 matrices. That is going to be extremely slow. So we found the issue, and I'm pretty sure if I step through this, yeah, we're gonna sit here for a while if we wait for it. Okay, cool. So calculating the determinant is the issue. So we need a better way to guarantee unitarity. And it's occurring to me that now I remember why we don't use a unit matrix, and it's because does a unit matrix? No, unit matrix should be. Let's do some Googling. Unit. It has a unit norm. Yeah. So we actually don't want a unit norm. Because a unit norm is not the same thing as being unitary. I don't believe. I think we worked this out already. Yeah, so the determinant is 1. That's not the same thing as being unitary. We want it to be normal. So any square matrix with unit Euclidean norm is the average of 2 unitary matrices. Interesting. So now we have a question, which is how do we guarantee unitarity if we're not doing this? Fast determinant. So Okay, so it uses the LU. Algorithm. LU decomposition, which runs in O to the n cubed. So in our case, n is like a million. So this is like 10 to the 18. Seems low. And if I look at this Strassen algorithm, it's O to the n 2.8. Okay, that does not strike me as a big speed up, so I don't think that's what we're gonna want to do. Okay, so one thing we could do is just if we're instantiating, if it's the identity matrix, we can just instantiate it. New matrix, D matrix, self. And I'm gonna call this new unchecked. So if it's the identity matrix, we can just do new unchecked. And that ought to speed things up, and that ought to immediately make our tests start passing quickly. Which it does. Our test now finishes in a quarter of a second. But we've not really solved our broader problem, which is that when we go to instantiate a matrix under any other condition, it's going to try to do this transformation. Also, this is not a function that we want to exist. So this matrix can also be unchecked. If we're tensor producting, it can be unchecked. If we're inverting, it can be unchecked. Okay. Okay, which is actually going to speed things up a lot, because now, actually we've handled most of our cases, because now our tensor product is unchecked. And we always build big vectors, either from identities or from tensor products. So I think this actually might do a lot of good. Git add all, git commits, use unchecked. Matrix, instantiations for known unitary functions, matrices. Okay. So I believe that will end up speeding up a lot of things. Let's go back to our biggest test and check how we're doing. Not fast. Okay, this is a surprise. Let's cancel that. And let's do it in the debugger so that we can see where it bottlenecks really quickly. So n qubits is 6. I got confused there. Okay, order finding. What? Oops. One more time. Okay, so the quantum Fourier transform instantiation is somewhat slow. It's not that slow, though. Identity is fast. Inverse Fourier transform does computes an inverse. That seems like it's going to be slow. Nope, not slow. Okay, apparently that's interesting. I'm surprised it could invert that fast, because it actually does an inverse. Okay. So circuit, add gate. Add gate is slow. Interesting. Why would add gate be slow? So we sort the qubits. That's fast, that's fast. This should all be fast. Getting the permutation gate should be fast. First 10 qubits should be fast. Ish. We are inverting a matrix. It's pretty slow. slow. Wow. Interesting. I'm surprised that the Fourier transformation being inverted was fast, but the reversing a permutation gate is slow. Okay. Well, we should be able to put our own permutation gate in pretty easily. So let's kill this. And let's just say pub function reverse permutation. And what we'll say is let qubit permutation be a new vector for ij in reverse qubit permutation. And we should just fill. Is there fill? I forget how this works. Zeros. And then permutation, qubit permutation. And let's say test permutation matrix. And let's say test reverse permutation matrix is inverse of permutation matrix. And we'll say let permutation be a vector, I don't know, 3, 1, 2, 0. And assert that permutation assert that quantum gate permutation let's say let expected be this, mute expected dot reverse, and then we will assert that quantum gate reverse permutation almost equals expected. Did not want that to be instantiated yet. Okay. Doesn't like zeros. What is the fill for vectors? Cross vector fill with zeros. With capacity. And this has been moved. Surprised I didn't get that before. Oh. Diverse. Failed. Index out of bounds. Oh, yeah, fair. 3120. No, not fair. What's going on? 3120. It's a 4-element matrix. Length is 0. Okay, so the problem is that it has no... Okay, it has a length of 0, but it has a capacity of 10. But we can do vec of 0, like that. And these are square brackets. Okay. Cool. Okay. So, and then we can take our reverse permutation and in add gate, not a function of a quantum gate. No, it's a function of a quantum circuit. And we now don't want to invert this. We instead want to use a quantum gate reverse permutation on completed qubits. Okay, and let's go ahead and cargo test everything. Oh, I guess this is gonna, well, this is failing for multiple reasons, apparently. This can be cloned. I mean, actually, can't these just be, these should just be references. I should not be cloning these all over the place. Yeah, that still works. Okay. Add gate permutation. And just a couple other places where our call site is wonky now. Okay. Whoops. Couple more. Okay. And now I want to run all my tests, but this test takes forever, so let's just comment it out for a moment. I just want to make sure as soon as possible, if I introduced some error that, okay, cool, tests are all passing. And let's see if add gate is faster now. Don't expect it to be lightning fast, but I expect it to be faster. And this doesn't really feel fast. Let's kill that. Okay. So, let's check. Do we have a new bottleneck, or is it still there? Those are fast. Those are fast. Okay. Why are we in... Oh. Never mind. Okay, so that was... Now it's just going to be slow. I can't have a breakpoint in add gate because it's going to trigger earlier. Okay, so these add gates are the potentially slow ones. And so let's jump into this. Head inline breakpoint. Is that a thing? Whoa! Wait, does this work? No, that doesn't work. Inline breakpoint. I don't know what that is. That could potentially be cool and useful, but... could potentially be cool and useful. Okay. I need to go into this function and see what's going on. Okay. Permutation is fast, reverse permutation is fast. Adding gates is fast. Tensor producting is fast. Composing gates is not fast. So this is like a 2 to the 6 matrix multiplication that's happening here. New matrix times a matrix. And these are square matrices. When we do matrix times matrix, are we new normalizing? Because that would do it. No, because we don't implement it ourselves. This is just regular old matrix multiplication. Wait, quantum gate. Oh, no, hang on. Okay. Matrix times matrix. Yeah, okay, that's the problem. So we are insisting that this be we were in our matrix multiplication, we were insisting that it be unitary, which was recomputing the whole unitary, doing the unitary checks, which again ends up not being a good idea, it would seem. So let's see if this is faster. Not feeling super light speed, is it? Okay. Let's kill that and continue our debugging. So, add gate. These are all fast. Compose. Okay, this is all it does. But it's still slow. Self.new. Just takes the matrix as is. This times this. These are square matrices. And that does an unchecked test, so does this. And yet, it's still slow. Okay, let's, oh. Wait, did it run? I actually don't know what, oh no, it's still running. Okay, let's put in a performance check on quantum gate. Like test gates compose. Quantum gates compose. And let's say let permutation equal 0 through, let's see here. Let size be 2e size power of 12 n qubits. Let's let n qubits be 10 or 12. So let it be 12. Range over u to size. Collect. And then permutation gate will be a permutation gate. Reverse permutation gate can be yeah, why not? And then I mean, this seems fine. This seems fine. Okay. So we expect this to be really slow because it's not slow, it just failed. Why did we fail? We're permuting 12 qubits, so this should be n qubits. And we actually don't, yeah, we actually don't need this. So this can just be this. And then n qubits, n qubits, n qubits, and we're happy. Okay, and now we have something to drill into a little better. Let's pull this out to make it easy. Okay. So the slow thing is just the matrix multiplication. That's not great. Let's test this. So, okay, so we think the slow-throwing thing is the matrix multiplication. Let's test this in our just an algebra test. Test 2 to the 10D matrix multiplication. To the 10 identity, let RHS equal matrix.clone. This doesn't matter. This doesn't matter. Matrix times RHS is matrix. And whatever, we can clone one more of these. Stopping my other test. Wow. And this is just slow. Interesting. So what this tells me is that the n algebra matrix multiplication on this many dimensions is slow. I mean, I'm sure it's faster than anything I could have written. It's doing like something like 1 million squared multiplications is the issue. Well, that's a little bit of a problem because we kind of need to be able to do matrix multiplication. Because we're going to have all these gates that need to get multiplied together. I mean, we can just run it for a long time, potentially. But that seems kind of anticlimactic. So if n is 2 to the 10, then we're talking about 1024. So 2 to the 10, 2 to the 30 is 1, 2, 3. So it's a trillion. So, all right. So the test passed, and it took 4 minutes. So it took 4 minutes to do it, something like a trillion operations. Am I surprised by this? 4 divided by 10 to the 30. Let's see here, how to think about this. There's a trillion operations. And it takes 200 seconds to do. Yeah, I mean, this doesn't seem crazy to me. Plus, there was copying because I'm cloning the matrix a couple times. Okay. And I imagine if I try to make the test if I try to do this test with like 15, then what is n qubits in this case? N qubits is 8. So we're going to have 10 to the 16 instead of 10 to the 10 to the 10. So 10 to the 16, I mean, it's 10 to the 16, which when tripled is going to be 10 to the 40, 10 to the 48. And 10 to the 48 is 10 to the 18 times as much as 10 to the 30. So 10 to the 18 times 4 minutes is going to be way too long. It's going to be way too long. Interesting. Okay. So here's what we will do. So I intentionally, when I'm building something like this, I purposely don't try to optimize anything because it's hard enough to get the answer right. Trying to get it right and fast at the same time is a recipe for trouble. You want to first get it right and then optimize. So we've gotten it right, but we have not optimized. So we're using the nice thing about our implementation of quantum circuit is that it just uses the same sized matrix over and over. Like, you figure out what the size of the circuit is going to be, and then you apply those matrices. The trouble is that those matrices turn out to be really, really big, and they're redundant, right? Like, a bunch of our, like, if we think about, I don't actually know what this is set up to do right now, but, okay, this is going to be a 4-qubit system, right? A 4-qubit system has matrices that look like this. There's a lot of black in these matrices, right? Those are all zeros. Those zeros don't need to be computed. We don't need to do multiplication. These are sparse matrices. So one thing you could do is use sparse matrix multiplication algorithms, which are presumably faster. I know they're a thing. I've never really studied them or thought about them myself. The other thing we could do, though, is instead of storing one big square matrix per quantum gate or per quantum circuit, we could do something that looks more like a circuit diagram. More like sorry, let me just try to find the there we go. Whoops. What to look for here? Right. Circuit diagrams, they don't have, like, this Hadamard gate, in some sense, is a gate that applies to all three. It's just the identity gate against these two qubits. But they only show it applying to the first qubit. And that makes this matrix multiplication way faster. And so I think that's probably what we need to do as well. And maybe we'll keep the current implementation of a quantum circuit as the, to use as a test, and we can call it, single matrix quantum circuit or something. But I think we probably want to kind of properly implement this, or not properly implement it, but implement it in, and I was thinking about this when I was first designing it, right? I was like, well, do I want to just have one big square matrix, or do I want to have kind of different operators applying to different qubits? And I picked the simplest one because I didn't want to optimize prematurely, but I think it's pretty clear that we need to do it this way instead. So the other thing we need to sort out at some point is how to do partial measurements. And I actually might do that first. Rather than starting to re-implement quantum circuit. So let's look at how that works. And I know that there's a nice interpretation of this. Okay, measurement 48. Of course, it's never actually 48 because PDFs. 46. 48. Okay. Measurement, blah, blah, blah. Measurement postulate, sure. What if I want to do it in a circuit? That's all I want to know. Poly observable Z, poly operator, quantum gate, observable, spectral decomposition. Measuring the observable, okay. Yeah. General quantum operations. Quantum computing. Okay, I want to find the word measurement somewhere in there. Qubits in the framework for quantum mechanics is not quite what I want. Von Neumann measurement. Simplest one is with respect to computational basis. Projective measurements are often described in terms of an observable. Measuring the observable corresponds to performing a projective measurement with decomposition I. An observable is an operator, M, acting on the state space of the system. This is the normal thing in quantum mechanics. Measuring the observable corresponds to performing a projective measurement with respect to the decomposition I. Yeah, this isn't quite helping me. Measurement is then made of the resulting state. Simple qubit by qubit measurement in the computational basis. Measurement of a single qubit is denoted by a small triangle. Okay, so I mean the point is to do a partial measurement. We just measure the relevant qubits. And I just have to work out the appropriate Born rule for it. Okay, so let's do this. So let's say in quantum register, I need partial measurement. Measurement, partial measure, self, and then a vector of qubits. And what? I mean, this is actually just let measurement, let measurement, new register equal measure. Let mute to return be 0 for I in qubits. To return is the measurement shifted to I. anded. Okay, so it's a little fun binary arithmetic that GitHub has put in here. So this is saying we take the measurement, which might be 0, 1, 0 or something, the complete measurement. We shift it, we right shift it, which is going to forget about all the bits, all the small bits, and it's going to shift the big bits over. So we're going to right shift it by whichever qubit we're talking about. So now we're going to have all the big bits, including the one that we want. So we're going to do binary AND with 1 in order to filter out only the first bit, because 1 is 0, 0, 0, 0, 0, however many 1. And so when we AND it with the bit string that we have, it's going to be a bunch of zeros and then either a 1 or a 0, depending on where, depending on the rightmost bit of this guy. And then we're going to shift it back to being the right number and interpret it as just a normal number, like a measurement, and add it back to return. And then we will return to return and new register. And I guess this should be partially measure. And I don't know how to test this. Sure I do. Of course I do. Test. Test. Quantum register partially register measures. And let's just say let basis 0 be quantum register basis, I don't know, 4, 0. Basis 1. Let's just get the, oh, you know what we can do actually? Let bases be quantum register bases 4. And then we'll say, what we say? Let's say for I in 0 through 16, let expected equal what to do. It's the nicest way to do this. I want to measure. I guess one thing we can do is say let measured be bases dot partially measure back of 0, and then we'll map that onto just M. Just pull the measurements out and collect, and then I want to assert that this is equal to 0, 1, 0, 1, 0, 1 all the way up. I wonder what the easiest way to do that is. Assert equal measure 0, 1. Can I repeat? Can I say repeat? Can I say into iter dot repeat? Can I do it 4 times? Nah, repeat isn't a thing. Rust iter repeat. Or do I just need to import it? Standard iter repeat. 4s, iter repeat 4s. I see. So I can do iter repeat and then this, but then I need to flatten. Nice. And then, really? All bases, all bases. And partially measure. Partially measure. Okay. Bases. Oh. Dot clone dot into iter dot map. Is that what I want to do? Yeah, I guess that's what I want to do. And we will do x dot. We will do x dot partially measure, and then map it. Okay. Measure doesn't know what type it is. It should be a vec of u8. And here we go. Whoa, why is it slow? Should not be slow. Oh. Yeah, I don't want... Okay. That iter is the number 4 forever. That's not what we want. We want the number 4 times. Or we want 0, 1 4 times. Failed. We want 0, 4 8 times. Cool. And if we do the same thing, but we do it on the third element, then we expect to get 0, 0. Then what do we expect to get? We expect to get this twice. Maybe? No, this 4 times. Because we're measuring... We're measuring 0. Yeah, we're measuring the third bit. And we expect to get it 4 times. I believe that's correct. We get 4s. Oh, sure, because every time that... Yes, every time that bit is a 1, then we should get a 4. Okay, so it's not repeating. It is just this, though. Okay, and then if we did it as, say, 1, 3, then we would expect to get 0, 1. So 0, 1. No, 0s and 2s mostly. Except a few of them are going to be more than that. So like this one is going to be 10. It's going to be 8 plus 2. This is going to be 8. This is going to be 10. This is going to be 8. This is going to be 10. This is going to be 8. Same story. 0. Wait, these should be 1s. And these should be 9s. No. That's not right either. This should be a 0. 0, 1, 2. 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh wait, these are gonna have an 8 in them though, so this should be an 8, this should be an 8. 11, 12, 13. Does 12 have a 10? Yeah, 12 has a 10 in it. 13, 14 has a 10 in it. Something like that. Not sure I quite did that right. But this is wrong. Missing a 2 here. Oh yeah, because 3 has a 2 in it, and whatever that is has a 2 in it. I'm getting closer, and I think I made the same mistake up here. But the point is, I believe this is correct. Okay, so that gives me a way to partially measure. All right. Kvikende says, "Hey, how you doing, Kvikende? I'm working on a quantum." A simulator for a quantum computer, and so just implementing a function that lets us partially measure a quantum register full of bits. Okay, let's commit this. Git add all commits. Implement partial measure. Cool. All right, so then the plan for next time will be to start in on the slicker interpretation of the quantum circuit, and we'll probably end up doing that to get Shor's algorithm to be faster, as well as we'll have to update our visualizations to visualize the right thing, because this visualization is not going to work if we don't have the complete matrices. I guess one nice thing about doing the circuit, the quantum circuit, sort of the right way or the more granular way, is that we can then render that quantum circuit into this view, not easily, but it doesn't require matrix multiplication. It won't require matrix multiplication. It'll just require tensor producting, because we can just take, at every layer in the circuit, we can take all of the individual matrices and tensor product them up to get a bigger matrix, and tensor products should be fast on sparse matrices. So we should get a, like, we should be able to run tests, for instance, that pretty much prove that the new implementation is the same as the old implementation by doing that tensor producting, which will be nice. Cool. I think I'm gonna wrap up there. I know it's a little early, but I don't want to get started down the road of implementing that quite yet. I think I will start that next time, which will be maybe over the weekend, or maybe on Monday. I will let you know. But anyway, hope everybody has a good weekend, or at least a good couple days, and I will catch you next time. Have a good one.